All right. Well, good morning. Happy Friday. We'll continue on. Just a little bit of, I guess, housekeeping or announcements. Monday's lecture will be pre-recorded. I'm not going to be here on campus. Okay, so I should say week 2 Monday lecture is pre-recorded. Do not physically go to class. There is no physical class meeting that day. Okay, so I'm going to just post a lecture lecture video. I'll probably record it right after this class, and that will be posted for Monday. I'm traveling to go see the eclipse. I'm going to try to catch the eclipse in Arkansas. My sister lives out in Arkansas. We'll meet up and try to drive down to, I don't know, Russellville or someplace in the path of totality. Hopefully we have good weather. I don't know, we'll see. And that's on my list of recommendations. At some point in your life, I recommend trying to go into the path of totality for an eclipse. It's a kind of it's a rare thing to see, phenomenon in the sky. I think in about 4 years there's going to be an eclipse in Sydney, Australia. So, maybe you have a desire to travel to Australia or something. But yeah, okay. Today we'll continue on. So on Wednesday we looked at linear regression, and and I said linear regression is an optimization problem. Okay. What we're trying to do is we're trying to find the slope and the intercept, or we call them the weight parameters, slope and intercept, that will minimize this quantity, the quantity being the sum of the squared residuals or the mean squared residuals or the MSE or whatever it might be, right? You have this quantity that we're trying to minimize. And to minimize a function, in this case we have 2 values that we need to search for to minimize the function. The function is sum of squared residuals. We have 2 values over which to search, the intercept and the slope. To minimize a multivariate function, you can use partial derivatives. And then we also looked at it using kind of linear algebra notation, matrix notation, to do kind of vector-based calculus and do optimization that way. And so that's where we're going to pick up today. We are still kind of working through linear regression, and we're doing it in matrix notation. And the reason why I start here is because I'm kind of under the assumption that linear regression is this concept that's familiar to us already, that we're trying, this idea of minimizing the sum of squared residuals is already familiar to you. And we start there because with this kind of familiar place, I can start introducing important machine learning concepts. So the next lecture, the one that, the video for Monday, will cover topics like regularization, or cross-validation, things like that. And those are concepts that appear in machine learning, and how do we talk about that? And so we do it in the context that's familiar, linear regression, and then the same ideas can then be transferred to other contexts as well. Okay, let me move my face out of the way here. So one important thing to remember is that when you calculate gradients, the gradient of a function with respect to a vector, the resulting gradient will have the same dimensions as the kind of input vector. So in this case, we want to find the gradient of this function. The output of the function is a single value, a single scalar value. So in this case, the sum of squared residuals, that's a single value. But we want to find the gradient of that single value, that function, with respect to the vector w. Well, the resulting gradient will have the same dimensions as w. So if w is a 2x1 matrix, the gradient of, say, w transpose x is going to be a 2x1 matrix, in this case X. Okay, X transpose W outputs a single scalar value. The gradient of that with respect to W is X. The W transpose W is also a 1x1 scalar, the output there, and the gradient of that with respect to W is 2W, which has the dimensions 2x1. And similarly, if you do W transpose matrix CW for symmetric C, and you take the gradient of that with respect to W, the result is also going to be a 2x1. So these are handy little helpful relationships. We left off here, I think, or I showed you this and I said, we did some work and we said the loss function, which is the sum of squared residuals, can be expressed as this, or actually this is the mean squared residuals because I've got a 1 over n here. The mean of the squared residuals is 1 over n t transpose t minus 2 over n w transpose x transpose t plus 1 over n w transpose x xw. And what we're going to do is we take the gradient of this thing with respect to w. This is the result. We're going to set the gradient equal to 0, and we want to find where is the gradient equal to 0. The location where the gradient is equal to 0 is going to be kind of a local min or local max or a saddle point, basically where there's you're at the top or the bottom of the hill. And so setting this equal to 0, we get x transpose t is equal to x transpose xw. We want to isolate w over here, so we want to get rid of x transpose x. Again, no such thing as division in linear algebra, but you can multiply by inverses, and so that's what we do. And you get this result: x transpose x inverse x transpose t is equal to w. And did you already cover this in 100C already in like your first couple lectures? Not yet. Okay, well this is coming up then. And so this is going to be a very familiar quantity, but right now this is the value of w. That is the answer to this question of what value of w produces has is the gradient equal to 0, okay? And that will then correspond to kind of the local min, or in this case, if it's just the squared residuals, it will be the global min there, okay? And so the estimate of our vector w, the weight, and again here the weight vector just collects the intercept and the slope together into this kind of 2x1 matrix. The estimate of that is going to be this, all right? And so let's just try it out. Here's a very, very simple data set. X has the values 1, 2, 3, 4. T has the values 1, 3, 2, 4. And so if I plot these, I got 1, 1, 2, 3, 3, 2, 4, 4. And we want to find out, I don't know if you guys can see that, what is the slope and intercept that minimize the sum of squared residuals? Stay here. So, if I said draw a line that fits these 4 data points and minimizes the sum of squared residuals, probably a lot of you would just kind of connect this dot down here, 1, 1, to this dot 4, 4, and you would draw this line, okay? But this actually does not minimize the sum of squared residuals. So you would get the sum of squared residuals here would be 2, I think. You have a residual of 1 between, like, the line predicts 2 when x equals 2, and the actual value is 3. The line predicts 3 when the actual value is 2. So you get 1 squared plus 1 squared, you get a sum of squared residuals of 2. The best fitting line is actually going to be something like this, okay? And you have a little bit of error everywhere. But the sum of squares residuals ends up being better that way. Because squared residuals punish big residuals heavier than a bunch of small residuals. But anyway, what we'll do is we'll go through and we'll figure out what our best values are for intercept and slope. So for the x, I take my column of x values 1, 2, 3, 4. I bind a column of 1s. Okay, so my x matrix is a column of 1s and 1, 2, 3, 4. And then I say, okay, what is x transpose x? X transpose x gives me this, 4, 10, 10, 30, a 2 by 2. I need to inverse that. The inverse of x transpose x you can do by doing solve, okay? Solve gives us the inverse in R. And so if I were to I get 1, negative 0.5, negative 0.5, and 0.2. And if I multiply that by this, you would get the identity matrix. And then so we're going to do x transpose x inverse x transpose gives me this. And if I multiply by t, x transpose x inverse x transpose t gives me 0.5, 0.8. So this corresponds to an intercept of 0.5 and a slope of 0.8. I can verify that these are indeed the slope and intercept of our best fitting line. I can ask R for give me a linear model. I can just say LM predict t based on x, and it says, yeah, your intercept is going to be 0.5 and 0.8 for the slope. Okay, so that's comforting to know that, like, when we ask R, I feel like we trust R when we do a linear model for figuring out the slope and intercept. And so we can see when we ask R to do it, it gives us 0.5, 0.8. When we do it ourselves doing this operation of x transpose x inverse times x transpose times t, we also get 0.5, 0.8, okay? And so we could say, all right, what are the values that you get when you have an intercept of 0.5 and a slope of 0.8? Okay, well, if you plug in 1, you get 1.3. You plug in 2, you get 2.1, 2.9, and 3.7. These are our predicted values. And so indeed, here is the line of predicted values: 1.3, 2.1, 2.9, and 3.7. Okay, and this gives us better results. Okay, so if we say what are the residuals here, it ends up just being a tiny bit different, right? The line that connects 1, 1 and 4, 4. You had no residuals at 1, 1 and no residual at 4, 4, but you had a residual of 1 squared here and a residual of 1 squared here. I guess squared residual of 1 squared and squared residual of 1 squared. Here, now the difference is 0.9 and 0.9, and if you do 0.9 squared, you get 0.81. And here your difference is 0.3, and 0.3 squared is 0.09. So here I have my squared residual is 0.09, 0.81, 0.81, and 0.09, and that adds up to a total squared residual of 1.8, which is indeed a tiny bit less than 2.0. So indeed, yes, this is gives us slightly better performance. Okay, and this is our best fitting line. So we can do the same kind of thing. Here's my Olympics data. So the Olympics data example was the 100-meter dash, and we're looking at the gold medal time. And what we see is that over time, it seems like the winning time has gotten faster, right? This is just kind of what it appears. We don't know if it's going to continue forever. I mean, certainly not forever. There's got to be some level off, but I don't know. You know, they release new shoes, they figure out new material to make the track out of and stuff, and I guess we can eke out a tiny bit of performance here and there. But this is what we have, and we might say, hey, let's fit a trend line to this data. So one we could just ask LM and see what our answers are going to be. So I could say, hey, predict the time using the year. And this says intercept 36.3, slope of negative 0.01328. Okay? In this case, the intercept doesn't quite make sense in that it would be what this corresponds to. What is our predicted time if the race was held in the year 0? Which, I don't know, I guess, you know, at the... yeah, if you go back 2,000 years or something, and if they had a foot race then. Did they have the Olympics back then? Maybe. They had the Olympics was what, an ancient Greek thing, and I don't know, was that around in the year zero? Maybe before then or whatever. Maybe they run, and we're saying, hey, we predict 36. But obviously, this is a terrible thing because this linear trend is not going to continue 2,000 years back. But anyway, if you plug it in here, we're just saying, as every year goes by, our prediction for the winning gold medal time drops by basically a little over 1/100th of a second. Okay, just a tiny bit, gets a tiny bit faster. Okay. So this is the answer of LM, 36.3, negative 0.013. Maybe we want to estimate it using our matrix operations. So I'm going to create my X matrix, column of ones. My X is going to be the different years. I do X transpose X inverse, X transpose T right here. T being the column of actual values. So I make Olympic $ time into a matrix. And indeed, I get the exact same numbers, 36.309 and negative 0.01327, right? Or I guess here it rounded, negative 0.1328. These are the values, okay? And so these coefficient estimates match what we got from LM. Let me go ahead and give you your first view quiz answer today. Is the letter A. A as in apple. A. First view quiz answer. All right, so to predict our values, we can just say, hey, let's plug in X, multiply it by our prediction matrix, W, I guess our predictive coefficients, which is just an intercept and a slope. And so we just do, 1 times the intercept plus X times the slope. Add those two together. That's what you get when you do X matrix multiplied by W hat. And these are all of our predictions. And we can plot that, and this is our straight line that fits our data. And go, okay, that looks okay. All right. What if we wanted to fit something nonlinear? Okay. So it's still a linear model. Okay. But you can have like a polynomial, right? If you have data that goes like this, and you fit some kind of polynomial relationship, that is still considered to be a linear model. Linear being you are doing a linear combination of the different terms, okay? One of the terms has a nonlinear relationship with the other terms, but the combination of those things are still linear together. So here we could do a polynomial thing. I could have a quadratic thing. I could just take my column of ones, column of x's, and I can create a new column where I just take x and I square it, okay? So I have a column of x squared values. And our prediction is going to be some constant multiplied by 1. That's the intercept. Some constant multiplied by x1, and some constant multiplied by this other column, x1 squared, okay, or our x squared columns. And so when you do a constant times each of these things and you add them together, that's a linear combination, okay? It just so happens that this column and this column over here, the relationship between them is that this is the square of this column. But if you just called this, say, y, or maybe not y, z or j or k or whatever, it's just a linear combination of these three terms. So it's still considered a linear model. And so I could do this using R. I could take a column of ones. I can take my X column, 1896, blah, blah, blah. And I can take X and I can square it. And I can have, you square 1896 and you get, what is that, 3,594,816. I take 1900 squared and I get 3,610,000, et cetera, et cetera. I get a column of x squared values. Okay. When we want to solve this, okay, my predicted values are now, I have 3 weight terms. I've got W0, the intercept, W1, the coefficient for x, and I have W2, the coefficient for our x squared value. if we express this in matrix notation, I could just say W is going to be the three terms, W0, W1, and W2. And each x value is now, 1, xn, and xn squared, okay? And so in matrix notation, our notation looks exactly like it did before. In matrix notation, we have just W transpose xn. If I write out the formula, now I have three terms. If I wanted to solve this kind of the old-fashioned way, using partial derivatives, now I have a system of three equations and three unknowns to solve, right? I have the partial derivative with respect to W0, partial with respect to W1, partial with respect to W2. I have three equations. I have to simultaneously solve all three of them. I set them all equal to 0 and solve. That's a lot trickier, okay? This is why we like to use linear algebra and matrix notation, is that once you have it in matrix notation, you can just keep adding terms and this part remains exactly the same, okay? And so because this remains exactly the same, my solution is going to also remain exactly the same, okay? So just to show you, xw does represent exactly the predicted value. If you have a column of 1s, column of x squared values, and you have W0, W1, and W2, I think we can see, yeah, that's my predicted value, W0 plus W1 xn and W2 xn squared. This is my predicted value. And again, rather than having to solve a system of three equations with three, for three partial derivatives, I just leave it in matrix notation. My loss function is going to be exactly what we had before, T minus XW transpose, T minus XW. And kind of going through the same process, we're going to end up with the exact same result, where my predicted value is going to be X transpose X inverse X transpose T. Right? Is that jump okay? That by using the matrix notation, I have a shortcut to get to this answer because it looks exactly the same as it did before. Okay, and so this would be I guess a major argument for using matrix notation, right? Sometimes when you introduce something new, students are like, oh, why do we have to use matrix notation when I'm comfortable with this other thing? Okay, well, there's advantages, and one of these things is that I could just keep adding terms and I don't have a more complicated system of equations to solve. All right, so this is what we have. My terms, my estimated coefficients are going to be found by doing X transpose X inverse X transpose T. Okay, so let's go ahead and try to do that. This is my I have my X matrix, which I've gathered column of ones, the column for X values and the column for X squared values, and I'm going to do X transpose X inverse X transpose T. I've got X transpose X times X. Inverse is, I do solve there, times X transpose times T, T being matrix Olympic dollar sign time. Okay, what happens? I run into an error. What do you think happened? So if I try to do X transpose X inverse X transpose T, I run into an error. And what does this error message say? It says error in solve.default transpose X times X, so X transpose T. System is computationally singular, reciprocal condition number. Okay, what does it mean for system to be computationally singular? Okay, something went wrong. We run into kind of these matrix singularities when either you have like columns that are linear multiples of the other or something, linear combinations of the other columns, or if you do something and you end up getting something like a 0 or an infinity or something. This is the problem. Okay, if you look at if I look at what is X transpose X, I have this. Okay, this is what I get, and what I'm trying to do is I'm trying to find the inverse of X transpose X. Okay, one of the problems is that my X squared values, remember I was taking things like the year 1900 or the year 2000 and I'm squaring it. So when you take the year 2000 and you square it, you get 4 million. okay? And then if you do X transpose X, you know, you're doing what? 4 million times 4 million, and what's that, 16 billion or something, okay? And then you're adding them up, you get a really big number. This is 4.09 times 10 to the 14th power, okay? All right, how do we, so you know, on one end I got small numbers like 28, and then on the other kind of corner I get these really big numbers of 4 times 10 to the 14th power. And I'm trying to find the inverse of this number, okay? When you find the inverse, it involves finding something like the determinant, okay? And then you're gonna, you have this constant where you're gonna do 1 divided by the determinant, okay? And what happens is now we're dealing with a number where we're basically doing like 1 divided by 4 times 10 to the 14, okay? Something, this really big number. And what is our computational limits? So some of you guys took 102A with me. Some of you did not have me for 102A. In your 102A class, if you did not have me as your teacher, did you guys talk about floating point numbers and like machine epsilon and things where, you know, you run into these things? So basically, the computer at its best, absolute best, can have up to around 16 decimal places of precision, like 10 to the negative 16, as far as you know, that's its approximate machine epsilon. And here we're just kind of dealing with these numbers, and we're kind of hitting up against that limit. And so the computer is not really able to kind of calculate values, you know, kind of smaller than this machine epsilon, and it throws an error to kind of, because we're hitting this computational instability, right? So then the computer says, okay, the matrix inverse doesn't exist. But that, you know, that's just not true. It's just, it's not able to calculate it because you're dealing with these giant numbers and little numbers at the same time, okay? So floating point numbers are great, but they're not real numbers, and so we run into problems. So just on a practical level, there's a couple things we can do. One is we could just scale down the numbers. So rather than dealing with, you know, 4 million, what if I just take that column of x squared values and I just divide everything by 10,000, okay? So now rather than 3,610,000, now I'm just gonna have 361, okay? And I have something like this. I can do this, and now if I take this as my X matrix, I have no problem doing X transpose X inverse, okay? So I'm gonna call this X scaled. This is my X scaled matrix. So I can do X scaled X transpose X inverse times X transpose T, and now I get values, okay? So this is, so we just have to keep in mind that this is the X squared values, but scaled down, okay? So now we have no problems. And indeed, I can kind of show you that if I did fit a linear model between Olympic $ time and the different columns in the X scaled matrix, we get the exact same values. So if I use LM in R to do this, you know, the values are 396.3, negative 0.382, 0.944, and exactly those are the same values, 396.3, negative 0.382, 0.944. So we get the same kind of things when we do our matrix operations with R. Okay. And now I can do my X scaled values multiplied by my coefficients. These are my predicted values, and this is the line that fits. And we look at that and we go, oh yeah, that looks like it's doing a decent job too, right? The thing is, I think our brains are easily influenced by a line, right? So if I showed you this linear line, you go, oh yeah, that seems to do a good job. And then I show you this line, I think you also go, oh yeah, that seems to do a good job too. Our brain just kind of likes to fit these things. Okay. One thing is we often recommend not creating a column of 1 x, and then just manually taking that value and doing x squared, okay? I mean, we saw some issues when we did just x and x squared because you run into these really big numbers that can lead to computational instability. There's another problem, is that if you just have, using just the example, like if you have 1 and x squared, you know, this is basically your x, and then your x squared values look something like that. And then if you kind of keep going and you do x cubed, basically you get this, and then x to the 4th, just kind of, well, maybe not straight up like that, but you just kind of get these steeper and steeper things. And one of the issues of just leaving it like that is you end up getting very, very high collinearity between all of these x quantities, right? X squared, x cubed, x 4th. When you start looking at these values, you know, you end up getting correlations of like 0.99, okay, between these things. And that leads to computational instabilities as well, right? So I think you learned what variance inflation factors and you don't even have to have perfect collinearity. If you just have high collinearity between your variables, you know, you have you know, the variance of your coefficient estimates just get inflated. And so one way to avoid that is to use this function called poly, okay? Poly will automatically kind of scale the values. And so for your range of x values, you're going to have, you know, your linear component, and then the quadratic component will look something like this, so that the correlation between the quadratic and the linear, the correlation here is going to be 0, okay? And then if you add a cubic, it's going to look like this, and the correlation between the cubic and the linear is 0. The correlation between the cubic and the quadratic is also going to be 0. And it kind of, if all it's doing is it's just kind of shifting things around so that the correlation between these polynomial components are all going to be 0, and you can isolate then the quadratic component or the cubic component or things like that. Okay, so that's going to be poly. So you can just do use this function poly. You plug in your x values, your vector of x values, and then you say, hey, I want you to create a matrix with a second order polynomial term. All right, and so you have this is the linear component. Over here is the quadratic component, and you can create a fit there, and so you get the intercept, the first order and the second order polynomial coefficients, and things like that. And again, you can you know, once you have a linear model, you can do your fitted values, and you get all of these terms, and you can plot them. Well, and anyway, you would get this quadratic fit. Let me give you your second answer. Okay, second answer is E. E as in elephant is our second Buchwitz answer. Okay. So yeah, when you use LM, okay, which is great, you can just kind of take the resulting model and you can just ask for the fitted values. Okay, and these would be all of the fitted values, and you can kind of plot that. Okay. One of the side effects of using poly is that all of the x values get transformed, so now your interpretability is much reduced. Okay, so these coefficients that we have for x poly 1 and x poly 2 no longer have the original meaning. Okay, we can't remember the original meaning was like, as each year goes by, our prediction for the time drops by like 1/100th of a second. Okay, now my coefficient is -2.5, and it's you know, -2.5 multiplied by this column x column that corresponds to x1, but these were all scaled somehow, and we don't quite know the scaling term that happened here. Okay, so now we lose this coefficient. But what poly is useful for is you kind of you use poly, you fit your model, you can do some kind of ANOVA analysis, or at least just see which coefficients are statistically significant, and then you can say, all right, we have evidence that there's a quadratic relationship that exists, or evidence that the quadratic relationship, or we don't have evidence that the quadratic relationship exists, or something like that. Okay, so using poly and LM together is useful in that we can kind of compare these different polynomial fits of different orders. We can create a whole bunch of these models and compare the resulting fits, even if we lose the interpretability of these coefficients. So just for fun, I can say, let's create a third order relationship, a fourth order relationship, fifth order relationships, and a sixth order relationship. And we've got, so I'm going to say, fit a linear model between, the time that we're trying to predict and our poly x3, 4, 5, and 6. Okay. And so here I'm going to plot all of these things. This one is, this shows just kind of our original, the dots. And then in red, we'll have the linear relationship. And then orange, green, blue, purple, and dark gray. This will be, linear, quadratic, so on and so forth. And what is the resulting fit? Okay, so we get this kind of this pretty graph, but, what's going on? So this is the linear fit. And the quadratic's in orange, and it looks like this. And the cubic is in green, and so on and so forth. And what we see is that all of these things get try to fit this one dot here out at 12. Okay, and so I don't know if any of these are actually doing a better job. We are adding additional terms, and so if we calculate like the sum of squared errors, I'm sure the sum of squared errors for each of these things is going down. But a lot of it also looks like it's influenced by this one value at 12, which I would consider an outlier, and I would actually suggest doing the analysis without this one dot, just because it feels a little bit out of place. Okay, and then if you take into context the context of the data, this was the time recorded in 1896. I think the first time they had the modern Olympics and things like that, and maybe measuring accuracy wasn't even around. Great. So, but anyway, this is what we have, and the question that we have now is, how are we going to pick which line does the best fit here? Okay. So 101A, you had this question of like, how do you pick how many terms to use, right? And you learned what? Forward stepwise, backward stepwise, using the AIC and the BIC. How would you, what does BIC do? If somebody asked you? It's like the Bayesian information criterion and the Akaike information criterion. But basically it's just, you have this thing, we're trying to minimize our sum of squared residuals. Every time you shrink that a little bit, your R squared values go up, R squared being kind of your model sum of squares divided by like the total sum of squares, and the more you get out of your model, that's better. But you have to kind of balance that out by saying like, oh, if I have too many terms, that's not great. So both of these things, the AIC and the BIC, apply what? Like a little penalty, like a penalty of 2 per term, or a penalty of log something per term, or whatever. And that can be used, sure. So here, if I say, hey, this is the model that I have for the third order polynomial relationship, we look at these things and we say, oh, it looks like it's significant in the first, linear, and the quadratic, and the cubic. All of these have p-values less than 1%, so it looks like they're significant. We'd probably keep at least 3 terms. if I go to say like the 6th order polynomial, we'd look at this and we'd say, you know, the 3rd order term is significant, but the 4th, 5th, and 6th order terms don't look significant. This was kind of our traditional approach. This is, I imagine this is the approach you guys used in 101A for determining which terms to keep, which ones to throw out, and stuff like that. Okay, and that's fine. That's a good approach. I'm not knocking that. But as we move forward and we do start going into machine learning, we are going to, the way we evaluate how things fit, we're not going to use kind of this traditional approach, okay? You know, one of the problems is if you use R-squared values, more complicated models will always outperform simpler models. You can always eke out a little bit of better predictive performance with R-squared. You know, we can use kind of the summary table and see, you know, which of these coefficients are significant. And, you know, moving forward, we will take into account some, use something called cross-validation. And, well, and then I guess we'll also introduce regularization. But cross-validation is probably one of the most important concepts as far as measuring how well our models do. And it doesn't take into account any of this kind of, there's technically like some theoretic stuff going on here, right? There's like an F distribution, or I guess these here are calculated using a T distribution. It's kind of based on this concept of, if we assume the residuals have a normal distribution, you know, how significant is our coefficient versus the residuals? And it relies on a lot of these underlying assumptions. Cross-validation just is kind of like, can we accurately predict values, is how it's going to be done there. So, so that's where we're going to be moving forward. So we start off, again, introducing these concepts and just showing you something that you're familiar with, linear regression, and then we're going to kind of just do a little bit of a twist and take linear regression and start applying, say, cross-validation to it. Okay, so that's going to be our next lecture. That will be, I guess, Monday's lecture, which I will pre-record and post, and I will not see you in class on Monday because I won't be here. But be on the lookout for that video. There will be a lecture view quiz for that video as well. So, so be on the lookout for that. Okay, I'm gonna stop the recording here, and I will give the people in person their 3rd view quiz answer. So we'll go ahead and stop here.